Okay, welcome to video 1.4. Okay, now I'm going to give an example of a likelihood function. Okay, so here, first, let's get some definitions. Um, we are going to write, okay, x sub I just equals the data for, actually, I'm going to call it x sub t. X sub t. The data for observation t, including the dependent variable. So, by the way, so I'm going to use the notation that Green uses. So you have some uh, pages that I've photocopied from Green, the econometrics textbook, and this is the notation Green does. So um, x sub t. So it will refer to observation t. Now this x might be a vector. Okay, so if it is a vector, the first element of that vector might be the dependent variable, and then all the other um, elements of that vector could be the independent variables. Now, usually in econometrics, we reserve y to be the dependent variable, and then the x's are the independent variables. So this is a little confusing. So Green and what I'm doing, we're going to use x to describe both the dependent variable and the independent variable. Okay. In fact, not only that, for this simple example I'm going to show you, I'm going to have no independent variables. So I'm going to have x is just going to be a scalar, and that scalar is going to be only the dependent variable. So it's going to be a little bit different from what you're used to. Okay, so I want you to get a little bit used to the terminology that Green is using. By the way, I'm giving a bit of a lecture. I want you to see this lecture before you start reading Green, because hopefully you'll see, like, why can't I understand this? Part of the reason is Green is using x to describe both the dependent and independent variable. Okay, that's a little unorthodox, and so I want you to see it first from me to understand that when you're reading. Okay, including okay. Now next, um, theta. We'll usually use in this course, at least especially in Green, theta will represent the parameters that we're estimating. Okay, and um, here I'm going to call it a vector of parameters. Okay, now usually in this case is we observe x. We see what x, that's the data we get. So we know that. Now theta is something we don't know. That's a parameter that nature has chosen. And often, in physics, they have these universal constants, c, that's the value of the speed of light, 186,000 miles per second, that is a number, a specific number. We may not know it exactly, but physicists have estimated that, to 7 decimal places, okay? Same thing can happen in social science. I think there's these universal laws, and there are these universal constants. They have things like the elasticity for demand of something, or one consumer's preference parameters. Okay, these things are chosen by nature. They are a specific number. We may not know them, we, the researchers, but they are a number. Now, usually the x's we will know, the thetas we don't, but we will try to estimate those thetas. Okay, now, next thing, we will write f of xi, we'll give semicolon theta, and that is, call that usually the probability density function, and then when that density function is discrete, we'll call this the probability of observing, I call it I. It's called x sub t. It'll be the probability that the data are equal to the value of xt, whatever we describe that is, given theta. Okay, so usually we write that when we write a probability density function, we treat it as if the parameter is given. That's already been chosen by nature, and then this x is including in the dependent variable it'll be a random variable. So we'll talk about the probability that dependent variable is a certain value, where that xt will be a certain number, but we'll treat it as if that theta is given. Okay, now when we get to likelihood, here's where we're going. A likelihood function will go the other way. It will treat the data as given and will treat this f as a function of theta. Okay, more on that later. Okay. So, but the key is that's a density function, and remember, when that dependent variable, that part of xt, is a discrete value, okay, not a continuum. When it's a discrete value, we'll call that f. We'll call that that will be a probability. Okay, it's a little bit more difficult when it's continuous. It's not quite, but it's very similar to a probability function. Okay, so now, and by the way, here's what else we will always do in this class, in my class. F is the probability of observing xt for that observation t. So now, often what we'll do, we will always do it in my class until you otherwise, we'll assume that these observations are independent. Okay, so more on that in a second. Okay, so now, okay, that's some terminology. Now, what I want to talk about now is a particular application of this terminology, and this is the Diermeier-Merlot paper. Okay, I'll write this Diermeier-Merlot. Okay. By the way, so I want you to read the green pages. I want you to read those very carefully. That's the thing I want you to take 10 hours on. The Diermeier-Merlot paper, that's the one, 10 minutes. Maybe more than 10 minutes, because we're actually going to use their data for a homework problem. But here's what Diermeier-Merlot, by the way, Diermeier, both of them are kind of like me. I call myself kind of a Rochester of political scientists, and there's kind of a tradition. There's the public choice school, and that's Buchanan and Tulloch, and then there's which were economists who started using economics tools to look at politics questions. Okay, there's something from the other side. It's people like William Riker. He's the main person who started, most people call the Rochester School of Political Science, and this was political scientists who are using economics tools to look at the political question. And they're a little bit different, although they met in the middle, and the Riker would usually go to the public choice meetings, and they talked to each other and got along, but it's a little bit different. There's kind of a different style. There's the Rochester School of Political Science, then there's the Public Choice School of Economics. My advisor was Keith Crable, who actually went to Rochester to get his PhD in political science. I'm often called someone from the Rochester School of Political Science. So here I am at the Public Choice School of Economics at George Mason. I sometimes compare this to the case of how, there's birds and there's bats. Now, they came from different trees of they have different ancestors. Birds, we think, came from reptiles. Mammals came from something else, but they each fulfilled a niche. In the niche, because of that niche, these animals evolved to do things like fly around. Now, they don't have their common ancestor. It is very, very distant. Okay, so bats and birds are very different. Now, but they look the same, and they do have the same kind of functions. They both fly around. Okay. I look at the Rochester School as something like the bats, and the public choice school as the birds. If so, what we have here is I'm the bat living among the birds. Okay. Um, Dearmeyer and Merlo are both kind of definitely Dearmeyer. He actually graduated from Rochester, and actually he's now, as I speak, he's the chancellor of Vanderbilt, and I think doing a great job. He was the provost of University of Chicago, but before that, he was a researcher doing what we do, public choice slash Rochester School of Political Science. So what Dearmeyer and Merlo do, okay, they look at a problem which was had to do with a lot of theoretical accounts of government formation in a parliament. And what people had done is they looked at this and they had asked the theoretical models had said, like, who is the formator? So, okay, how is a government formed in a parliament? And the models usually said, well, there's a formator. And what this is it's the first party. Often it's chosen by someone like a king, or various ways. It's the formator is chosen in different parliamentary systems. But a lot of these models would assume that the party with the most number of votes is always chosen formator. And they're given the opportunity to form a government. If they can't, then the second biggest party is given the chance to form a government. And they can't, third biggest, and so on. And then some other models said, well, what if instead of assuming that it's the biggest party, instead it's chosen probabilistically, where the probability that someone is chosen formator is proportional to their number of seats. Okay, there are different theoretical models that made different assumptions about who is the formator in a parliamentary system. And Dearmeyer and Merlo said, well, let's look at the actual data. Let's see who is the formator. Is it always the biggest party, or is it looks like it is equal? The probability of being formator is equal to your share of seats in the parliament, and that is what their paper does: is try to estimate these two different theories and try to estimate which is more accurate. Okay, so that is what that paper is doing, is it's trying to determine how a formator is chosen. Okay, and what we're going to do, we're going to have first consider a very simple version of the question they ask. And the first, what we're going to do is we're going to set theta. For this case, we're going to define theta equals the probability the largest party is selected formator. Okay. And then, okay, so that's our parameter. Okay, it's going to be a probability that the largest party is selected. Sorry, my ring light is making a reflection off this. Okay, here. Next, okay, xi, or x sub t, that just equals, in this model, equals 0. Call it 0, 1, 1, 0. Wait, take what? Make it simple. 1, xt equals 1 if largest party is selected formator, 0 otherwise. Okay, so I told you this x sub t data. So for the teeth observation, it could be a vector, say a number of elements. I said the first of the elements will be the dependent variable, let's say, then the rest of them will be independent variables. In this model, this very simple special case of the Diermeier-Merlot model, x of t is just a scalar. So for observation t, there are no independent variables. There's just one dependent variable, and it's 0 or 1. That's the dependent variable, whether in observation t, say country t, whether the largest party was selected formateur or not. Okay, so that is, okay, that's our model so far. Okay, next, often what we'll have is, so that's small x, we might have big X, we might call that the universe, and big X equals possible values of each xt. So in this case, big X is just equal to 0 or 1. Okay. Okay. Now, a likelihood function. Okay, wait, by the way, okay, let's say, so in this case, x of t is discrete, okay? So I said when x is discrete, that means the probability density function is a probability, okay? So that means in this case, so if we look at sum over all the possible values that xt can be, okay, so that means xt is either 0 or 1 of f, wait, okay, I'll get to it. Xt theta, that has to equal 1. So if we sum over all the possible values that x can be for f, they've got a sum to be 1. And the reason is because, first, the way we've defined f of x, by the way, if x of t is 1, so that means in this case f of 1, so it's probability xt is 1 given theta, that's the probability that the largest party is selected formateur, and we're defining that, in this case, that just equals theta. Okay, now the probability that the largest party is not selected formateur, that we would describe that just as f of 0 theta. Okay, so given this setup, the probability that the largest party won't be selected has just got to be 1 minus theta. Okay, given that, you'll see that f of xt summed over all the possibles of values of big X, it's just got to be, that must equal theta plus 1 minus theta, and so that must equal 1. Okay, that's where that comes from. Okay. Okay, so that is the basic setup. Okay, so now, here's what I'm going to do. I hope everyone can see this. If you want to hit pause, I'm going to erase this. Okay, so now, okay, suppose we have 3 observations. So we have, so xt is going to be just x1, x2, x3. And let's assume, okay, so remember x1, that's the dependent variable, it's 1 or 0, whether the largest party was selected formateur in observation T. Let's assume we just have, this is a cross section. We only have 1 year's worth of data. So this is 3 countries. Okay, so we have 3 countries. Let's assume that in the first country, country 1, largest party was selected formateur. In the second country, assume the largest party was not. In the third country, the largest party was. Okay, so that is our data. 101. Okay. Now, when you read green, okay, and always in this course, we're going to define the likelihood function. In the likelihood, so as Flew said, it's the probability of observing the data given theta. Okay, so it turns out our likelihood, and we're going to make likelihood, we'll always make it a function of the parameter we're estimating. So I told you, usually with density functions, usually we talk about it's the probability of observing the data given theta. So it's a function of the x's given the theta. Well, with likelihood, we do the opposite. We're going to say, we're going to treat the data as if they are given. Okay, so we're given the data, and we're going to say, we're going to make the function, the likelihood is going to be a function of theta. Okay, and we define it to be the probability of observing the data we observe given the theta. Now, I told you all the f's are going to be the density function. We're going to assume all these observations are independent of each other. Okay, so we define, in this case, the way we would define the likelihood function, this just equals the probability of observing the data that we do given the function. So this is just going to be, we have 3 observations, so it's going to be f of x1 given theta times f of x2 given theta times f of x3 given theta. Okay, where I can use that time, that's where the assumption that they're independent comes in. Okay, these observations are independent. Okay, now, if you recall from the last board I made, f of, well, okay, we can actually, let's substitute in what our data is. So this equals f of 1 theta times f of 0 theta times f of 1 theta. Okay, all I've done is just substituted in x1 equals 1, x2 equals 0, x3 equals 1. Okay, given that, and then if you look back to that former board before I erased it, we can just substitute for these f's. Okay, f of 1 theta just equals theta. F of 0 theta, so it's probability that the largest party will not be selected, that just equals 1 minus theta. And then f of 1 theta, again, is equal to theta. Okay. So that is our likelihood function. Theta times 1 minus theta times theta. Okay. Let me do something kind of foreshadow what we will be doing in this class. Okay. We can rewrite this. This just equals theta squared times 1 minus theta. Here's one thing we'll do. We're going to use calculus. We'll say, and so Flew talked about, so there's some good properties when we pick the theta that maximizes this likelihood function. So how would we do that? Well, we use calculus. The theta that maximizes it's going to be where we'll get a minimum or maximum. But if it's going to be the maximum, the derivative has to be equal to 0. Okay, so we can just say L the derivative of theta is just going to equals, use the chain rule, that equals 2 times theta times 1 minus theta plus theta squared times -1, and that equals 2 theta minus 2 theta squared minus theta squared equals 2 theta minus 3 theta squared. Okay. If we set that equal to 0, okay, that equals to 0. Okay, so that implies 2 theta equals 3 theta squared. Okay, let's divide both sides by theta, and that gives 2 equals 3 theta, and that says that theta equals 2/3. Okay, that's the value of theta. Turns out we can take the second derivative to show that it's a maximum rather than a minimum, but theta equals 2/3 is the value of theta that maximizes that likelihood function. That's pretty intuitive because we have two cases where the largest party was selected, one case where it wasn't. 2/3 of them, the largest party was selected. So it's kind of intuitive that a good estimate of theta, the probability that the largest party is going to be selected formateur is 2/3. Okay, so we've done our first case where we've maximized the likelihood function. We're going to call our maximum likelihood estimate of theta is 2/3, and it should be pretty intuitive. That it should be 2/3. Okay. Okay. Next, let me explain finally something that Flew described. Okay, Flew. How am I doing on this one? Oh man, 27 minutes in. Okay, this one's going to be long. Flew said, okay, with likelihood in connection with the statistical chance, this likelihood does not give directly the probability of the hypothesis because the sum of the likelihoods of variable hypotheses may be much greater than 1, or I also told you it might be less than 1. Does not necessarily have to equal 1. Here's what I mean by that. Okay. Here's what we have. So we have our likelihood function, L, this equals theta squared times 1 minus theta. Let me rewrite that. Okay. Oops, sorry. This equals theta squared times 1 minus theta. Okay. Now, let's use let capital theta. Okay, circle with an H in it. Okay, that's the best I can do for writing the capital version of the Greek letter theta. Let theta equal all the possible values of theta. Okay, well, we might say, well, it makes sense to say it's anything between 0 and 1. But let's say it wasn't true. So suppose that somehow nature gave us a clue, said, no, we can rule out certain values of theta. And suppose that we knew, some magic genie came down and said, nature has chosen the true value of theta, but I'm going to give you a clue of what possible values it could be. And let's say that the only two possible values are theta equals either 1/2 or 3/4. Okay. So, wait, I don't understand why that could be. Well, suspend your imagination for a moment and say that some magic genie came down and said, look, trust me, okay? I've seen what nature have chosen, and it's, either 1/2 or 3/4, okay? Flew writes, the sum of likelihoods of rival hypotheses may be much greater than one, or it could be less than one. So this is the idea of rival hypotheses. Okay, that theta. We'll talk about the null hypothesis, alternative hypothesis. Suppose there's only two possible hypotheses: theta equals 1/2 or theta equals 3/4. If we summed all the rival hypotheses, that would mean we would sum over all theta, over all the possible values of theta, of L of theta. Okay, so if we do that sum, here's a theta, that Flew talked about, here's what we would get. We would get, the first case, it would just be L of 1/2 plus L of 3/4, and that equals, okay, let's just substitute in 1/2 for there and then 3/4 for that. So we're going to get 1/2 times 1 minus 1/2 plus 1/2 squared plus 3/4 squared times 1 minus 3/4. Okay. And hope you'll trust me, if you do the arithmetic, you get that this term equals 1/8, and then that term equals 9/64. And that is less than 1. Okay. Now I could have chosen a capital theta of, a whole bunch of other possible values that would have made that sum greater than 1. Okay. But I chose one case. That magic genie just said it was only one of these two values. In that case, it could be less than 1. The key is, depending on what the genie tells you, it does not necessarily, that sum will not necessarily be 1, and it almost surely will not. The genie would have to pick them just right. So in fact, usually when the genie picks the possible values of theta, the sums of the rival hypotheses, the sum of the likelihood is not going to equal 1, and that's what Flew means when he writes that. Okay. So this is lecture 4, okay? And there's maybe a couple more points I'll make. That will be in part 1.5, and I'll see you there.